Where does the term carbohydrates come from?
It has carbon, hydrogen, and oxygen.
Good. How is this different from hydrocarbons?
They just have carbon and hydrogen.
Good. What's the main purpose of carbohydrates? Their main function?
Their energy storage.
Good. What's a pretty popular secondary function other than energy storage? Think like cellulose.
Start. No. It's not a thing.
So cellulose is what gives plants rigidity. So structure is actually another pretty common use. Okay. So a lot of these that we talk about are saccharides. What does the term saccharides mean?
Sugar.
Yes. Okay, we can have mono, di, tri, technically, or polysaccharides. Okay. What do those terms mean? What are they referring to?
How many sugars, I guess? Like how many saccharides are part of the chain?
Good, exactly, yes. So how many are linked together? So mono, you just have the singular saccharide. Di, obviously two. Poly, many. You can have smaller, like you might see oligosaccharides. Basically, that's just like an in-between. So it means like a few. It's like not really a clearly defined number per se. What are the links called that link them together?
Acetal bridges.
Okay, good. Do you remember another term for these? Starts with a G. You might not have focused on it because that is more glycosidic bonds.
Oh yeah.
Did he talk about that?
No.
Okay. It's more big picture, I suppose. Good. So acetal bridges. So what does the term acetal mean? We talked about this. What's the functional group, acetal?
It's like an alcohol in an OR group.
Close. So I think that. Hello.
How's it going?
Good. How are you?
Hanging in there.
We just barely got started. We're just kind of on the first page. So we're talking about the linkages between saccharides, acetal bridges, and we're reviewing the functional groups hemiacetal and acetal. So you said an alcohol group and an OR group.
Yeah, that's hemiacetal.
It is.
So it's 2 OR group?
Yes. Okay. The tricky part with this is you don't normally see carbohydrates written this way, right? So this is a simplified version of it, but if we're trying to locate that okay, so where is the hemiacetal? Oh,
It's right. So the O and then there's a C on both sides.
exactly. So if I were to color code this a little bit better. And I should switch these. And then OR is just an oxygen carbon bond. So there's our hemiacetal. So this hemiacetal is converted to an acetal when we create a glycosidic bond. Let's see what that looks like. So we're going to remove this OH group. So here we have our second OR. Okay, you see how we went from hemiacetal to acetal there? Good. Okay. I wouldn't worry about drawing these. It's more about identifying them. Okay? Okay. Taking a step back. That was kind of a jump forward. Sorry. So, saccharides can be classified in a couple different ways. One by their functional group. What are the two different functional groups that saccharides can have?
Like aldose, ketones.
Okay, good. So if they have an aldehyde group, so we're going to have a carbonyl group and a hydrogen. That's referred to as an aldose. Ketone, that carbonyl group in between two other carbons, ketose. What's the second way that we can classify saccharides? Number of carbons. So if I have the smallest carbohydrate that you can have is something that's 3 carbons long. That's referred to as a triose. The OSE refers to it being a carbohydrate. Tri obviously refers to the number of carbons. So what do you think a 4-carbon carbohydrate would be called?
Tetros.
Tetros, exactly. So pretty simple. I would also be comfortable combining these two. So if I had something like this, you should be able to name it. So typically the name goes so functional group, number of carbons, OSE. So how would we name this carbohydrate? Exactly. So 1, 2, 3, 4, 5 carbons. Aldehyde group, aldopentose. Any questions on classifying that way? Okay. Again, this should all be fairly review at this point. Okay, chirality and optical activity. Let's keep this example here. How many chiral carbons do I have in this carbohydrate? Bless you.
Three?
It is 3. And it's actually easier than you would think to figure that out. So what I just drew is called a Fischer projection. And by definition, when you're drawing a Fischer projection, anytime there's a cross, that's a chiral carbon. So these 3 carbons that I didn't draw out, you can automatically assume that those are chiral carbons. So he may ask you to identify that off of a Fischer projection. Because we have chirality, we're going to have 2 different enantiomers. Okay, so you can have either D or L enantiomers. How do we figure out if this is a D or an L isomer?
where that, like, OH is? On
Good.
the second
Yes.
to last one?
Yes. So it's always going to be the second to last carbon, or the last chiral carbon. Okay. So the OH group is on the right. That refers to D. Pretty simple to remember. Okay. I would definitely expect at least one question about DNL isomers. Which isomer is mostly found in nature? D. Good.
I feel like you explained that so much harder in class. You made that so complicated.
Okay. Another term that you may have heard it before. You'll hear it again if you take biochemistry.
Is that what Dr. Shapiro?
Yeah, so he does biochemistry. Dr. Davis does another version called biological chemistry. Essentially, biochemistry requires the organic prereq. So you guys would be able to take that, but people that don't take organic can take biological chemistry. It's just slightly different.
So if you have a ketone, how does the chirality work with a ketose?
Sure. Let's see here. And so this would be an example of a ketose. So essentially, you're going to always have two CH2OHs because you can't have the carbonyl group on the end. So there has to be another carbon here. And so there has to be two H's there instead of the one H. So you'll still have 3 chiral carbons here. Is there a more specific question that you were asking?
So it's still going to be the same, you just don't count the carbonyl for a ketose.
In terms of chiral carbons?
Mm-hmm.
Yeah, so you wouldn't ever count the carbons on the end or the carbonyl group because for them to be chiral, they would have to have 4 separate attachments, or not separate, different attachments. These two obviously have 2 H's, so there's some form of symmetry there. And the carbonyl group only has 3 attachments. It doesn't have 4. So you can't, these 3 cannot be considered chiral.
Okay.
But the drawing will still be the same. You'll still have crosses for any chiral carbons if he's drawing Fischer projections. Does that answer your question?
Yeah.
Okay. So let's take a look at these 2 right here. Very, very similar carbohydrates. But we have one difference. This middle chiral carbon, the OH group has been flipped. Okay? Everything else has stayed the same. There is a specific term for this. So when you have 2 diastereomers, because these aren't mirror images anymore, with only one difference, it's referred to as an epimer. It's just a very specific type of isomer. Okay? I don't know if you talked about glucose and galactose. They are epimers of each other.
You mentioned it, yeah.
Okay, so that's just a real world example. So instead of drawing, he might just mention glucose and galactose. So that's kind of a memorization piece, knowing that those are epimers of each other. Okay. Also remembering that the chiral carbons here are also considered stereocenters. Knowing that those are stereocenters, how many isomers can you make from this molecule?
So it would be just the 3 chiral?
Yep, so there's only 3 chiral, so there's only 3 stereocenters.
So
Okay.
2 raised to...
Yeah, 2 raised to the 3, exactly. Good, so just remember that formula. That's really the review for straight chain carbohydrates. Any questions on that? Because we're going to move to the cyclic form. Okay. So again, I kind of jumped ahead, but just to say it again, when we're talking about our cyclic carbohydrates, they are hemiacetals. When we were talking about that chapter, when hemiacetals and acetals first were brought up, the chapter made a point to say that acetals are considered more stable than hemiacetals. Typically, hemiacetals aren't really stable at all. This is an exception to that rule. So when we're talking about our straight chain, okay, because carbohydrates can flow back and forth, there's an equilibrium here. The straight chain is much less stable than the hemiacetal. So in this form, hemiacetals are fairly stable. Still not more stable than an acetal, like the acetal bridge. But sometimes that can be confusing if you look back in your other notes. So this is a stable hemiacetal. So this doesn't happen very often, but it is really stable. So typically you're going to form what number ring, like what member ring would you expect to be formed? 5 and 6. We know that from organic chemistry 1. Do you guys remember what it's called when you have a 5-membered ring? Pyranose. These markers are not happy. And a 6-membered ring? Pyranose. Why would the pyranose be more stable than a furanose?
Less ring strain.
Exactly. Okay. There's a special name for this carbon here. It's referred to as the anomeric carbon. Markers are annoying me. Okay. Depending on the orientation of this OH group, you can have 2 different anomers, which are again a type of isomer. Okay. So if the OH is in a downward orientation, that's referred to as an alpha anomer. If the OH is in an upwards orientation, that's referred to as beta. I don't know why chemists decided to put alpha on the bottom. Couldn't tell you. Carbohydrates can open and close. Like I said, they flow back and forth between a straight chain and a cyclic form. So technically you could have an alpha glucose, for example, open in water and then close again in a beta form. It is possible for it to flow back and forth. It's not stuck in either of these forms at this point. When it does go back and forth, the name for that is mutarotation. So I would know that term. Okay, any questions on the basics of this?
So the alpha form is an anomer and the beta form is an anomer?
They are anomers of each other, yes.
Oh, okay.
Good question. Okay. the next type of carbohydrate is called a glycoside. Bless you.
Thank you.
This is referred to as a sugar acetal. Essentially, what we're going to be doing here is we're going to be changing the hemiacetal to an acetal, but we're not going to be actually linking. So we're still going to have that acetal functional group, but it's not going to necessarily be in the form of linking the two together. So essentially what they do you tag a methyl group onto that oxygen. So again, this is still an acetal group. We have one OR here, one OR here. When we do this, we essentially shut down mutarotation. So by making this an acetal group, this ring can no longer open and close. Did he talk at all about reducing sugars? No.
I don't know.
Okay. So, depending on who you had for your general chemistry, you should have talked about a concept called reducing sugars. And essentially, when you have a sugar in a straight chain form, okay, we have our functional group here. If it's an aldehyde, we know that we can oxidize an aldehyde group. What do you get when you oxidize an aldehyde?
Like a carboxylic acid.
Carboxylic acid. We removed a carbon-hydrogen bond, added a carbon-oxygen bond. So if we can oxidize something, that means that this can reduce something else. Because remember, whenever you're oxidizing, reduction has to be happening somewhere else. So if this is possible, this is referred to as a reducing sugar. It's just a term that's used for it, okay? If you can't oxidize a sugar, so for example, if we had a ketose, like maybe fructose, would you expect to be able to oxidize that ketose?
Wouldn't it be more difficult because it's not terminal?
Exactly. So you technically can't oxidize a ketone, okay? So what basically happens is there has to be some sort of reorganization here. That's a totally different process. The main point is, unless you have an aldehyde group, you can't oxidize it. So typically ketoses are not considered reducing sugars, okay? So when we're looking at glycosides, so let's say that this is glucose. We know that glucose is an oxidizing sugar, or sorry, reducing sugar. It can be oxidized because it is an aldose. If we block glucose from opening up its chain, okay, because we've formed an acetal here, it can no longer be a reducing sugar. We can't oxidize. There is no aldehyde group to oxidize here. So we can't oxidize it the same way as when it's open. So glycosides make it so sugars cannot be reducing sugars. So glycosides or sugar acetals are made when you acetylize or add a carbon group to that oxygen. So you turn a hemiacetal into an acetal. This closes the ring permanently, it can't open back up, and makes it so sugars cannot be reducing sugars.
So you add a methyl group, you said?
Yeah, so this is just an example. Technically, it could be any R group. But that's the most simple form of it.
So it just locks the ring, basically.
Exactly.
Okay.
All it is.
So it makes it so it can't reduce.
Yes.
But it's not like a protecting group, right? Because it's like...
Yeah, I wouldn't really consider it a protecting group. Because technically you're saying that you're protecting the OH group, but that would be assumed that you'd be reacting somewhere else and then removing that, which you're not really, that wouldn't really be the purpose of this. Are you ready to go on to key reactions? Okay. So some of these you may remember. You should have completed some of them in your regular chemistry class. So the first two, Fehling's and Tolling's tests, we've also talked about them, was it last semester? I can't remember now. Both of these test for reducing sugars. Basically, you perform this test. If there's a reaction, then that means that that sugar was oxidized, which means it's a reducing sugar. Okay? So the premise is the same. The actual reagent is really the only thing that's different. So Fehling's test uses a copper base. Tolling's uses silver. If you have a positive result in Fehling's, you're going to expect a red precipitate. In Tolling's, you're going to expect a silver. The next two are involved with oxidation and reduction. So the first one. So with this one, essentially you've got pieces being broken off. Okay, and depending on what they start out as, that's going to indicate what type of final product you're going to make. So let me explain what that means. So let's say we have, I believe this is actually fructose. Okay, so here's our fructose. We're reacting with a reagent. I don't know if you talked about it. I don't think that the reagent is necessarily of high importance. I would more focus on what's being formed. So our two outer groups, the CH2OHs. These are going to be oxidized. So if we have alcohol groups, what do you think they're going to be oxidized to?
Aldehyde?
exactly. So we have one carbon. That's our aldehyde group. The only other attachment is a hydrogen. So what's the common name for a one carbon aldehyde?
Formaldehyde.
Formaldehyde. So we are making 2 formaldehydes. If we look at our carbonyl group, it already has 2 carbon-oxygen bonds. Sorry, yeah, 2 carbon-oxygen bonds. This is actually going to become fully oxidized. Do either of you remember what the most fully oxidized form of carbon is? Carbon dioxide. So we make 1 carbon dioxide. These 3 groups are actually turned into carboxylic acids. So oxidative cleavage, the cleavage, we're breaking off, or essentially breaking all of these carbon-carbon bonds, okay? And then each piece we're oxidizing. Because we are slightly different in the bonding, we're going to end up with 3 different groups of final products. So again, we're going to end up with formaldehyde, carbon dioxide, and some carboxylic acid. Okay, reduction in monosaccharides. So if we take, it could be any monosaccharide, but I think glucose is probably the easiest one. So again, we have an aldehyde group here. Knowing what you know about reduction, how do you think this monosaccharide is going to change when it becomes reduced?
Make an alcohol.
Okay, good. So the aldehyde group at the top, that's the only functional group that's going to change here. Sometimes students get confused and they want to start changing these OH groups down here. So the only thing that's going to change is the aldehyde group. Okay, so we go from an aldehyde or an aldose to an alcohol. Did he talk about sugar alcohols at all? What's the word for them? Like sorbitol or xylitol? I don't know.
Yeah, he gave examples.
He did, okay. So I would just keep those in mind. He could ask you for an example. I don't necessarily think that that would be a first question, but he might talk about one, in a question. So really what he's talking about here is this. So a lot of times these sugar alcohols are formed because they don't, they're not oxidized the same way in the body. So people use them as like alternatives to sugar. Okay. Any questions about oxidative cleavage or monosaccharide reduction?
He did want us to know the name though, the alditol.
Alditol. Okay, he did make a. Okay.
Yeah.
All right, that's good to know. Other than that, okay. Let's move on to the next 2. I don't know how much he focused on this one. I don't necessarily think that this one is the most important reaction for you to know, but we will go through it. Essentially, you have sugars reacting with what are called phenyl hydrozones. So our aldehyde might convert into something like this. Sorry for this marker. Okay, I do want to point you to this C6H6 here. Okay, the reason that this is called phenyl hydrozone. Did he show any pictures of these at all? No.
I don't know.